Welcome everyone, this is Fred Schenkelberg, and this is the SNDO webinar series with a combination of quality and reliability topics and invited speakers. And I'm very happy to have Stephen Wax with us today. Stephen's going to talk about sample size and the impact it has on control charts, which is a topic, to be frank, I didn't really pay much attention to before. I was almost always constrained by how many samples I could take, and or if I wasn't, didn't think about its impact. So the little bit of pre-work Stephen and I did is whet my appetite to this topic. Stephen's got a lot of experience. He's worked with Ford Motor Company. He's now a principal statistician with Integral Concepts, where he works very closely with his clients in doing statistical methods, reduce variation. He's got experience in reliability analysis, design of experiments, and statistical process control. And I know Stephen from a couple of years ago, we did a series of tutorials that were very well received and very sought after, even in the recorded form. So welcome to everybody today, and welcome Steve for doing this webinar with us today. I should also mention that Steve and I are also in the works of creating a course. So if this just whets your appetite for this topic, or you know of people that would like to learn a lot more about SPC and process capability, stay tuned. We're going to share a link for signing up for the course, and we'll send out more information on that if you're interested. So without further ado, let me hand over to Steve and let you get started. I'll take a moment here for the slides to come up. And as those do, I should also mention for all the participants, we're going to have a chat window open and a question and answer window open for almost the entire presentation. And we're expecting you to contribute, to add to your experiences, your questions, and we'll try to address and discuss this with you as we go through it. So I'll be in the background managing some of that, but I look forward to the discussion and the dialogue. And so Stephen, I think your slides are up. I think we're ready to go.
Great, thanks Fred, and welcome everybody to the webinar today. Hope the weather's good where you are today. It's not bad here in Michigan for a change. I think spring has finally hit us here after a long wait. So I'd just like to reiterate one thing before we get started, and that is, as Fred mentioned, we're planning a course, and part of this talk today was not just to provide information to everybody, which is of course a noble cause, but we're trying to perfect, or at least get work on the process of getting interaction with the participants. Obviously, when you do online training, it's quite a bit different than face-to-face, where you can see people and ask questions and sort of pick on people. But so we're hoping, I just want to reiterate that I really encourage your participation, both through questions, the chat window as well. There'll be cases where we ask a question and open up the chat window for you to respond. So there'll be a couple opportunities for that that we'll be requesting today. Before we get into the material, I'd just like to briefly recap the agenda. So there's 5 topics listed. The first 2 I would say are sort of background material. The purpose of this is to try to get everybody up to a level set. I realize that with 20 plus participants, there's probably a wide variation in the amount of knowledge that exists with regard to SPC. And the topic for today is, I would say, sort of something that's not basic. I mean, it's an issue that comes up that probably should be talked about more, in my opinion. But I thought before we jump into specifically the sample size issue that we should at least spend 7 to 10 minutes just providing sort of some background on the very basics of control charting and what SPC is all about. So that said, well, again, I'm always going to encourage questions. If there are a lot of questions on this early material, I'm probably going to have to defer some of it, just because I don't want it to turn into a basic overview of SPC. We have a very kind of targeted topic, and that's all about the impact of sample size on detecting process shifts. So with that said, I'll go ahead and just run through this agenda quickly. So the first one is just a quick overview of the purpose of control charts and key concepts. we're going to talk a little bit about what happens when we average data, and there's a big difference between what individual data looks like with regard to variation versus when we start averaging and looking at subgroup statistics like X bars or averages. And then we're going to get specifically into the main topic, which is all about, one of the purposes of a control chart is to detect process shifts, and it turns out that the sample size has a big impact on that. So we're going to take a look at exactly what do we mean by a process shift and what kinds of errors might we make, and what is the impact of sample size. We'll also go through some simple calculations on determining sample size, and show you how that works. And then finally, I'm going to show you a tool, a graphical tool, to more or less capture alternatives for designing a control chart and taking into account the risks that are inherent of not detecting important shifts in the process. So I think at this point, Fred, we're going to actually do a quick poll here just to get some understanding of where everybody is today. And you may not know the answer to this. That's why it says there's an option here that says I don't know. But here's the question. It says, how does your organization, or this could be you if you don't know what your organization's doing, how does your organization currently determine the sample size? And by that I mean the subgroup size. So when you collect data for charting purposes, you might take a certain number of groups of data and then chart those on your control chart. But within each subgroup, you could take one, which would make it an individual's chart, or more than one. So the question is, if you're doing subgroup charts, like X bar charts, how do you currently determine the size that you select when designing that control chart? So I'll go ahead and let you read the 6 responses, and we'll just wait a couple minutes and see what we get, and then we'll recap it.
All right, we're off to a good start. Got about 3/4 of the people have responded so far, but and it looks like it's going to be a race between I don't know and we always use 5 or some other fixed number. All right. So is that a surprise, Steve? No,
it's really not a surprise, because I ask people this when I consult or do training in SPC, and very commonly the answer is we use 5. I think perhaps maybe in one of the AIAG manuals it suggests using 5 as a good number. And as we'll learn in this topic, that may be appropriate, or you may want to consider doing something larger, and maybe even significantly larger, depending on the application. And maybe 5 is going to be too large for our purposes. So yeah, it's not surprising at all.
Okay, great. So let me bring you back to the slide deck.
Okay, so like I said, for the next couple minutes, I'm just going to try to provide a brief overview of SPC. So I thought I'd start off with, well, what's the purpose of control charts? So probably could come up with more than 3 items, but I think these are the main ones, right? So we want to, a control chart is simply a tool. It's like a diagnostic tool of what's happening to the process, and it allows us to monitor key process characteristics, certain aspects of the process, such as the average, where the process is running on average, or the variation. And the point of this is to detect when process changes occur. So when the process actually changes versus where it's run historically. So the key thing here is this is not an inspection tool. We're not measuring things and comparing to spec limits. What we're doing is we're coming up with a baseline based on some initial data collection, and we're sort of determining how does this process typically perform. And then from that point forward, we're looking for changes. And the whole idea here is to detect by detecting a change, we can usually react to a situation much more quickly before it actually goes out of spec. So again, this is number 2 here. It's all about preventing issues rather than reacting to them. I think probably most of you would agree that many of our companies, we probably spend too much time firefighting or reacting to problems, and less time actually working on prevention. So control charts is very much a tool to help us prevent issues. And then finally, we'll start talking a little bit later about types of variation, and specifically the control chart is attempting to identify when a so-called special or assignable cause of variation is occurring to the process or system, so that we can identify it and hopefully correct it and eliminate it from occurring. We're never going to get rid of all the variation, but the hope is, at least from a control perspective, that the variation that we're contending with is primarily natural, expected, or what we call common cause variation. So I want to spend a couple minutes here and talk a little bit about what do I mean by an in control or a stable process. There happens to be, I find a lot of confusion around some of the terminology in SPC, whether it's capability, stability, in control, out of spec. There's sometimes people get sort of turned around on the terminology, so I'll try to set that straight here. So by stability, because I like to think of it this way. Suppose I collected a whole bunch of data over a very maybe short period of time. Of course, I'd have to have a reasonable amount of high volume process, but suppose I collected a fair amount of data. This is a radius of, say, a component that I produce many of them. And I draw the distribution, which is really just the way the data stacks up. And suppose that the distribution looks like this. And for those of you working with quality, this clearly does not look bell-shaped. And that's not a concern of mine because much data doesn't happen to follow a bell shape. But so this distribution sort of describes where we tend to see measurements fall out, and we can see that there's a skewness to this data set. So more importantly, when I think about what happens later on now, suppose I repeat this exercise at various points in time in the future, maybe 2 hours later, and then 2 hours again, and 2 hours again. So each one of these curves represents what my process looks like every couple of hours. And if we basically see that the process distribution is more or less looking the same over time, then sort of conceptually we call that a stable or an in-control process. Okay, we're certainly not going to get the exact same data values from sample to sample, but really what we're saying is that the shape should look fairly similar. The overall central tendency, where does the process tend to run most typically, should be fairly consistent. The amount of variation in the process within each sampling period should remain fairly constant. If that's true, then we say the process is in control or stable. Okay. Notice I'm not saying anything whether we're in or out of spec. I mean, this process could be half in spec and half out of spec, but it would still exhibit a stable or an in control process. It's basically predictable. As opposed to a very different picture where we see when I start to draw these distributions which describe my data, I see sort of very chaotic behavior. The whole process is shifting. Some curves are narrower and taller than others. So this is what we call an unstable or an out of control process. It might be that everything here is within specification, but it's certainly not a predictable or stable process. Okay. Now, so how do we relate this concept to the control chart? So obviously we don't have time to sit here and draw pictures of distributions all day long. So what we do is we sample from the process over time, and we construct a chart called a control chart, which is a tool that, again, as I said, allows us to sort of observe what's happening over time. So when I say a sample, I essentially mean I take a group of measurements. I might just be one. Sample size could be one, but in this case, the sample size is 5, which was your most common response. And we take this sample and we calculate some statistics, which more or less describe where this process, the behavior of this process at a point in time. So the average here describes the location of the process, and the range in this case, or possibly a standard deviation we might do, describes the amount of variation within that subgroup, which is really, again, an estimate of the short-term or common cause variation of this process. So once we do collect enough of these samples, we'll then have enough information to set up an overall average and some limits here that we call control limits, which are what I like to call limits of expected variation. They're basically what we expect to see given the behavior of the process during that data collection period. And if the process is stable, those actually represent reasonable limits of expected variation. Okay, so the reason I wanted to show this was that when we talk a little later about sample size, I'm talking about this sample here. Should I pick 5 or 1 or 10? Okay. And of course, once you, again, as I mentioned, once you collect enough of these subgroups and plot the relevant statistics, the averages, in this case the ranges, we'll have enough data to estimate the overall process average, the control limits for both the location chart, in this case the X-bar chart, and the range chart. And we aren't going to get into the mechanics of constructing charts in this talk. And hopefully, if we've done everything correctly and we've designed the chart and constructed the limits correctly, and we've paid attention to sample size and have a good understanding of what kinds of shifts we're trying to detect, and we've minimized our errors, the hope is that when this process changes, so let's suppose that number 4 were shifted to the right by an appreciable amount, that the next point we plot on the control chart would reflect that shift, because it would potentially live up here beyond the upper control limit, representing that this process shifted. Okay, so again, this control chart is a tool we use to detect changes in the actual distributions of our process. Now, one more slide, and then I'm going to open this up for a little bit of interaction. I mentioned earlier common and special cause, and I threw those terms out. So just to come back and formally sort of define those loosely. By common cause variation, I'm referring to variation that's normal or inherent part of the process. It's generally difficult to control. It results in randomness in our data. I'm not saying it's always acceptable. It's very often the amount of normal variation is not acceptable, but it's sort of typical. It happens all the time. A special cause, on the other hand, is something that's not part of the system or regular process. It interjects itself into the process maybe periodically or one time, and it results in a significant change in that distribution. Perhaps it causes a shift or a trend in the average that we're seeing from our data. So it's something external. So what I'd like to do then is just to kind of illustrate this and drive this point home, is open up these two chat windows. And the question I thought about, should I have you just throw out aspects of your own processes? And I thought, gee, with 20, 30 people here, we'll get a lot of very specific answers. So I know not everyone here is probably not a golfer. I myself am not a golfer anymore, but hopefully you can think about this. If you're standing there driving a golf ball, perhaps at a driving range, I think everybody on this, if you are a golfer, you probably observe variation in how far or how straight you drive the ball from drive to drive. And I think that's the variation in that process is something that every golfer contends with. So think about potential causes, common cause variation and special causes of variation, and let's list a few. Okay, I'll make a few comments on a few, and Fred, feel free to jump in as well. So yes, certainly this skill level, someone who's highly skilled is probably going to have less variability than someone who has a lot. Fatigue, right? So some days you might go to the driving range and be fresh and be hitting them long and straight, and other days you're more tired and maybe not keeping your eye on the ball. Poor grip, right? So if there's grip to grip differences every time you strike a ball and you're not holding the club exactly. I mean, think about it. If everything was identical every time you struck the ball, meaning you stare at the ball for the same amount of time, your feet were in the same exact position, you shifted your weight exactly the same, you used the same club every time, your mechanics of swinging were the same, everything was the same, and you hit the ball in the dead center every time, that ball really would travel the same distance every time. But obviously that's not going to happen. Humidity, right, so if you're golfing on a hot day, you may lose your focus trying to wipe the sweat off your face. Let's take a look at some of these special causes. Okay, Fred, so Fred says strong headwind. Yeah, so I would say if you go out one day and you golf with the wind at your back or with no wind and you hit 50 drives, and then the next time you go out you're driving into a 20-mile-an-hour wind, that would very much likely change your distribution. It's going to shift everything. It's not something that's just random drive to drive, but it's going to be a consistent impact on the process. George is saying cracked club handle. Absolutely, right? So if on one day your handle is not cracked and the next day your handle is cracked and you lose the force through the ball, absolutely. George says his mood goes down during every game. That's what happened to me, and that's why I gave up the sport. So I think we've got this. Fred, do you have any comments?
No, yeah, I mean, you're illustrating though that there's normal variation, the common cause stuff, and that's the small change in our muscle response to swinging the club, the overall conditions that day that are consistent with every time we swing. All those kinds of things are common causes. I would argue that with George, if it happens every time you go golfing, then that's probably a common cause that you see a decline in distance as you. I find that if I have one good stroke and I get a good distance, a good strike on it, my mood goes up and I'm good for the next 2 holes, and then I go back into the slide. But common causes is more, I like the one that cracked club handle, right? Or if the grip comes loose, or and I actually had one where I thought I was getting a hole in one, and a duck landed and blocked the ball on the green. But yeah, I think there's different causes, and what I'm looking forward to is then how do I pick my sample size such that I can detect these things accurately and sort this stuff out. I hope that's where you're going a little bit with this.
Right. Thank you for that transition. So good. Thanks for your input, everybody. I'm sorry I couldn't address everyone, but when we think about manufacturing, of course, the examples are different. We think about common maybe being as temperature fluctuations or normal sorts of raw material variation or differences in dimensions of components, everything within spec, versus maybe a change in a supplier of its key component, and they're actually running, have a different design, and might produce a very different sort of response in our process. So just to kind of sum this up, we looked earlier at this picture similar to this, and I called this a stable process. So the point here is that when the process is stable, the only source of variation that's acting on it is common cause, as represented by the variability under this distribution. And when we have an out-of-control process, right, we have multiple sources of variation acting on the process. We have common cause, which we always have, plus we have apparent special causes or assignable causes here. So again, the purpose of the talk is to really think about how do I detect these special causes, and that's the whole point of the control chart. And one other term I thought I'd mention here as part of the background is just bringing in capability. We've mostly been talking about stability, but capability has to do with how well does the process meet specification. And the point I wanted to make here is that it's a separate sort of concept. Stability has to do with are we predictable, consistent? So both of these two processes on the left here represent stable processes. One of them is very capable and one of them is not, okay? And then on this side, neither one of these are stable. You might argue conceptually this one is capable because it is meeting specification, but I would not encourage anybody to calculate CPK or PPK or PPMs on this sort of a process, because by its very nature it's chaotic and unstable, and any quantitative assessments you would get would be not very predictive of the future. Okay, so that's sort of a very quick background. How are we doing on questions, Fred? Are there any things we should address at this point, or charge ahead?
George asked a good question. I think from the interaction on the common and special causes, he noted that sample size may not always catch special causes. His question's more on, does sample frequency play into this also? And I don't know that we're talking about sample frequency, but if you could address that as we go through, that would be great.
Yeah, towards the end, I'll bring up frequency. It's actually had a part of the talk, and I took it out because it was just, I didn't think we'd get to it. But yeah, I'll come to that.
Okay.
All right, so
George,
go.
George, I'll take your question live here so that I can remind Steve later to make sure he addresses it. And for anybody else, feel free to type in your questions as we go. We'll get to those, as many as we possibly can, and or use the chat window. We're watching both those things.
Okay, so the second sort of just background idea I wanted just to get across before we get into the sample size question has to do with just really what happens when we look at averages versus individuals. So I picked this simulation example, and really it's not really a manufacturing process. I wanted to start with something that was very non-normal. In this case, it's represented by a uniform distribution. But basically what this represents is, suppose I take a deck of cards, and I take a card, and I read the value, and then I put the card back, and I do it again, and I repeat this 13,000 times. And let me just tell you, an ace is worth 1, and then 2 through 10 are worth, obviously, what the value is on the face of the card. And then a jack is 11, a queen is 12, and a king is 13. So basically, there are 13 possible values. And the reason this is straight across is that the probability of seeing any of these cards is, of course, the same, 1 in 13. So that's what the individuals look like, and I actually ran a simulation, and of course I didn't get exactly, this was only 1,300, not 13,000. I would expect 100 of each, right? But I didn't quite see that, but I did see relatively flat distribution, certainly nothing that's bell-shaped. But now I want to do this a little differently, and when of my 1,300 picks, I'm going to basically take 2 at a time. So I'll take 2 cards, and actually I'm going to put the first one back before I draw the second, or to be more efficient, I would take one card from each deck and average the values. And then down here, I'm actually plotting the value of the average. So whereas on an individual card, I can't get 8.5, certainly on an average, I can get 8.5. So that's why there's a little more continuity to this distribution. But even with just a sample size of 2, we're sort of seeing that the shape of the curve, which was very flat, is now becoming somewhat bell-shaped. And I'm not sure if you can tell what's happening with variability yet, but in fact the variability is decreasing. And of course what I want to do is just keep playing this game and seeing what happens as the sample size increases. When I get to sample size of 5, again, the distribution is becoming sort of more bell-shaped, and we have less occurrences of averages in the tails. In other words, the curve is getting taller and skinnier, okay, versus with n equal 2. Now it's possible to get an average of 1. I could get ace, 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 like shown here. I just didn't see any in 1,300 trials. The probability is too low. The reason the probability is, excuse me, is higher in the middle here, and thus the curve is higher, is because there are many more combinations of 5 cards that will give me an average of 7 than a 1. Right? The only way I can get a 1 is ace, 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 ace. Where 7, there's many combinations of cards that will give me that. So conceptually, that's sort of what's going on here. And I can play this game forever, and as my sample size increases, we're noting that the distribution of those sample averages is getting tighter. And that's really going to be a key fundamental point with how we address sensitivity of control charts. And that's just a summary of what I've been talking about. Mathematically, the relationship's actually quite simple. For those of you that are familiar with the statistic called standard deviation, it's a measure of variability. It has a formula. We won't get into it here. But we can talk about the standard deviation of averages, basically a group of averages of some sample size, versus the standard deviation of individuals, which I've shown here with the sigma without any subscript. And it's a very simple relationship. The standard deviation of the averages distribution is simply the standard deviation of the individuals divided by the square root of n. So clearly, as n increases, this standard deviation of averages decreases, and that's why the distributions of averages was getting tighter as n increases. Now, I just want to take an opportunity to give you a chance to respond to another question here in the chat window. So it's sort of related to what we've been talking about. Given what we've just talked about, or what I've talked about, related to individuals and averages, and how the variability is very different, I'd like you to take a look at this chart here, this control chart, where I've plotted some averages, some sample averages, and some control limits, which again are the limits of expected variation. And it looks like this process is stable. And I've also put the specification limits for this characteristic on the chart. So I'd like to hear any comments. Given what we've talked about, do you see anything that's troublesome about this chart? Maybe it's okay. Maybe you think everything looks fine. It looks stable and capable, but what are your thoughts here? So I'm expecting to see a few things as it's telling me multiple people are typing. Okay, George says the potential drift. Now, we could get into some of the signals, the number of points. Something a little more fundamental I'm looking for here. You know, we have to be very careful about overreacting to a few points trending upward. I wouldn't really call that a trend yet.
You see Kyle?
Oh, Kyle? Yeah, okay, so good, Kyle. And Pat, I was waiting for you to speak because I know you teach this material and you've been into too many of our classes. But yeah, both Kyle and Pat, I'm trying to read as fast as I can here, but Kyle says spec limits have nothing to do with SPC, and he's correct. They certainly have nothing to do with control charts. Pat says individual measurements may be out of spec, but you'll not be able to see it on the chart. And that's really the point I'm trying to get across here is this is a chart of averages, X bar chart. This represents some average of maybe 5 measurements, okay? And the control limits represent the limits of expected variation among a subgroup of 5, okay? This says nothing, these control limits say nothing about where the individual values fall. In fact, if I actually look at the more data, the data that was used to construct this chart, I'll see that the sample size was in fact 6. 1, 2, 3, 4, 5, 6. These were the 6 measurements that made up this average, and I picked a few other points here. And clearly, a good number of points are actually well outside the spec limit. Process is not capable at all. So this is one of these things that we talk about in the training, and unfortunately I see a lot of charts sometimes that have spec limits on them, even though they're charts of averages, and it's really mixing apples and oranges. It ties to this topic because it really, the reason that these spec limits are not appropriate is because we can't compare individuals which have spec limits which pertain to individuals and reflect allowable variation among individual measurements with averages, with X bars, which in control limits, which are just about averages. And as it turns out, the reason we use averages in SPC a lot is that they're far superior for detecting shifts, and that's the whole point of control chart, is to detect process changes, not to determine whether we're in or out of spec. So again, I apologize I couldn't get to everybody's comments, but glad to see a few people were right on it, and we'll go on from there. So just as a process check, we're about halfway through, so we're going to kind of quickly get into the meat and potatoes of detecting process shifts. Okay. Now, I worried about showing this slide here because there's probably somebody in the group who's going to send me a nasty email afterward and say, hey, this control chart stuff is not a hypothesis test. You know, didn't you actually read what Deming said and how he said it's not a hypothesis test? I get that. I understand it. I like to use this as a model because no one can deny that when you're using a control chart, the purpose is to detect changes. And also the purpose is to not get a bunch of false alarms, right? We don't want all these signals that mean nothing to us. So by its inherent nature, the control chart has, if it's not constructed properly, can fail to detect important changes. That's called a type 2 error, and there's a probability associated with that called beta, which is 1 minus the power, if you like power instead. But that's when the process, we decide the process is in control. In other words, we don't see any remarkable signal, yet the process actually has gone out of control. It has shifted by an amount that we really would have wanted to know about. On the other hand, we could also make a type 1 error, which is the process is actually in control, but we actually conclude it's out of control because we happen to observe a signal that was a sort of a fluke, right? So again, I realize we can have a debate about whether this is really a hypothesis test or not, but I think the concepts behind hypothesis testing apply to a control chart here. So what I mean by this, let me just see if I can just draw a little picture here. Not. Okay. What I'd like to do is just kind of illustrate in the context of a control chart what I'm talking about here. So suppose, and I apologize, these are obviously supposed to be horizontal, and it doesn't really like when I do dashes, so imagine these are dashed lines and they represent control limits. Maybe I have to do them more straight. And okay, there's a distribution and not supposed to look normal. One of the things we saw in that little simulation I did is that when you average data, the data tends to form a bell-shaped curve, and that's something called the central limit theorem. We won't get into the details of that here, but so let's suppose the process is stable and the process is running. The average is on this straight line here. Fred, I think next time we have to just set these up ahead of time. But anyway, it's certainly a question then, is it possible to see an average that lives beyond the lower control limit from this process? And the answer is yes, because control charts, you know, we construct these control limits to be to capture a certain proportion of the statistics that we're charting. It's usually about 99.7% if you're doing a 3 sigma chart with normally distributed statistics such as averages. So because it's not 100%, we may see some signals beyond this lower control limit. That's called a type 1 error. What I really want to talk about in this webinar is what happens when the process does shift. So it shifts from this top curve to the lower curve. And again, this is a distribution of averages, the first one and then the shifted one. And the question is, following this shift, am I for sure going to see a signal? So when I'm starting on my control chart, I'm not really observing these distributions. I'm just looking at points on control charts. So if I get a average at right here, let me use my mouse a little easier. If I get an average that sort of lives down here, below the center, but not below the lower control limit, the question is, it may have come, or could it come from this shifted curve that goes from here to here? And the answer is, of course, yes. So this sample average may not come from this top distribution, it may come from this bottom distribution. Okay, and if this was a shift from this mean to this mean was something that we would have wanted to know about, I've now committed a type 2 error because I'm not going to react. Now eventually, of course, I will see something down here, or I'll get a run below the center line, or some of these other signals that you might be familiar with. So I want to take a minute and just kind of illustrate what I meant by a type 2 error. It's when the process shifts and yet the next sample doesn't actually tell us that we've shifted. Okay. Now a couple key points about the subgroup sizes. So it's going to turn out, as we'll see in a minute, that the sensitivity or our ability to detect these shifts will depend on the subgroup size, among some other things. And what we want to try to do when we design a control chart is think about, what does our process look like now in terms of its variability, and how much variation can I really tolerate? In other words, if the process were to shift, by how much can it shift before I would want to have a high probability of actually detecting that? Now, that's not really a statistical question, it's a practical question. I have to think about how much variation can I tolerate, and how capable is my process today? If we can take just a minute or two, I'd like just a few people, or as many that can type it in. Someone give me an example of where they've determined a practically significant change in the process as opposed to statistical changes. So if we can go to the chat window, does anybody have any ideas on what do we mean by a practically significant change?
The meeting is now over. All the participants have been disconnected.
Sorry about that. I think hopefully everybody's still online. Steve, you still there?
Fred, I'm here.
Okay. And if somebody could, yep, Mike says we're still here. All right. Something going on with my audio bridge. So I restarted it and hopefully we're all back. So Stephen, back to you. We'll get back on target. You're asking for input on what's a practical change.
And if you want, you can think back to the golfing example and say, how much of a, if you could go out and purchase a $300 new driver, how many additional yards would you need for that to be worth the money? Like, are you going to go out and buy a new driver if it increased your average length of your drives by a half a yard? Or do you need a bigger impact?
You make drivers that'll let you stay on the fairway?
Yeah, that what people would pay anything for. 100 yards? Yeah. Okay, yeah. So, in the sake of time, hopefully if anyone else types in, I'll try to catch it. But by practical, we have to think about, from a risk perspective, from a customer perspective, what would happen if this process variability changed or the average changed? If I'm borderline capable, right? My CPK is, very right on the edge. I'm probably going to be more concerned about smaller process shifts than if I'm highly capable and I'm, got lots of room in my tolerance and the variability within that inner part is not very critical. I may not want to know about very small changes. So that's going to guide how big of a shift we actually look for. Wear-induced drift in a part dimension, okay. So we'd have to think about how much drift on a wear would be something that we'd be willing to tolerate. Yeah, certainly, Mary Ann, absolutely. If customer specs are not going to be met, so you could work backwards from knowing what the process average is and what the variability looks like and figure out, all right, how much room do I have for a process shift before I would actually be out of spec. I mean, that's the bottom line right there. So very good. Okay. Now, so let's get to this. I'd like to just kind of go through a quick example of this, how this all works. So if you remember the simulation, we're going to leverage this idea that when I average data, the curve gets tighter, the curve of the distribution of my averages. And I'd like just to run through this example to kind of illustrate the point, and then we'll look at the formula. So suppose I'm filling up containers of ice cream, and the label weight is 16 ounces. Okay, so the label weight's actually down here, and because I want to be responsible, I'm going to actually center the process above the label weight. It turns out my filling process standard deviation is estimated to be 1/10 of an ounce. So if the filling process is normal, that basically says I'm going to be mostly filling between 16 and 16.6. And so the first question I have then is how much of a shift do I want to, if I set my process up to run at 16.3, how much of a shift in the process average do I want to detect, right? So I might say, do I want to detect a shift down to 16.29? Okay, probably not. I mean, could I do it? I mean, I could do it with enough data, but that's probably not worth knowing about. All right, so we have to think about how much risk we're willing to tolerate of underfills. And so let's just say, for purposes of this example, that I've determined that I'm willing to tolerate a shift of 0.15 ounces. So that turns out to be about a 1.5 standard deviation shift in this case. And if the process shifted that much, I can see down here that I would have at least some portion of my new process distribution falling below the specification below the label weight. And it turns out in the food industry, you're allowed to have some as long as none are too far below some maximum level of variance. Now the question is, as my control chart can actually detect a 1.5 sigma shift, what if I tried to be cheap and just get away with individual measurements? So I would do what's called an individuals chart. Okay, and you can think of this as a control chart turned on its side, where normally the data you'd look at goes from left to right. I'm going to show it going like up to down, and you can imagine this normal curve would be turned 90 degrees. But if I were going to try to use individual measurements to detect this shift from 16.3 to some hypothesized shifted process, the green curve, the question is, do I have enough power to actually observe that shift? Well, if the process doesn't shift, I'm basically going to be seeing values between 16.0 and 16.6 that fall under the purple curve. Now, if the process shifts to the green curve, the question is, where am I likely to get my next sample from? And it's going to now come between here and about 16.45. Most of that green curve still lives within the control limits of the purple curve. So I'm very much likely not going to detect that change. In fact, if you do the math, it's about a less than a 7% chance that I'll see my next container below the lower control limit. So I'll commit a type 2 error. I'll fail to detect that process shift. Now, if I increase the sample size, things start to get a little better here. So this is a picture of what happens when n equals 2. So as we saw earlier, when you increase the sample size, the standard deviation of our averages decreases. That means our control limits, which are 3 standard deviations of averages, is now tighter. Size of the shift hasn't changed, but the original distribution and the shifted curve are now tighter curves. And we're going to ask the same question. If the process shifts from purple to green, what proportion of that process will fall outside of the control limit, meaning what proportion of the time am I actually going to see a signal below that lower control limit? Now, certainly I've improved. I'm up to 19%. Okay, but in this case, let's suppose I want to be 98% sure that I'm going to see a signal on the very next sample following a shift as much as 1.5 standard deviations. I'd have to keep playing this game a little bit longer. 5 isn't going to do it for me. Finally, when I get to 12, I see that this overlap, in other words, this area under the green curve that falls within my original control limits is less than 2%. So I've now found a sample size that would allow me to detect this change on the next sample. Now, some question earlier had to do with frequency, so I'll just maybe try to address that here. Obviously, I'm being kind of rigorous here, and I'm saying, what's the error on the first sample? For those of you doing SPC, you know, we take repeated samples, and the frequency is a big part of this, right? So if I'm taking frequent samples, I may not be so concerned about a larger type 2 error on any given sample if I'm going to be sampling very frequently. Some processes are very disruptive to sample from, so in those cases I would want to ensure that my individual type 2 error probability is very low, that there's very little chance I won't see the change. We could play a lot of probability calculations about playing with frequency and probability of not detecting and how many is it going to take and those kinds of things. We would do that perhaps more when we have more time in a training seminar. Hopefully the idea is fairly clear. Essentially what we're talking about here is that by increasing the sample size, I allow the control chart to discriminate between the assumed stable process and something that has changed. Okay, I can now detect this shift with higher probability. Now, while I'm continuing, if there are any specific questions about that, you know, please go ahead and type them, and we'll catch them. If not during the last couple topics here, or during the Q&A afterward. The next couple slides just give you a little information about how would you actually calculate the sample size given the various parameters that it depend on. And the key things that sample size is going to depend on is the process, first of all, the process standard deviation. If I start with, just back up for a second here, if I start with a lot of variation, for me to shrink that curve down, I'm going to have to increase the sample size by more than if I start with already a tight curve. Hopefully that makes sense. So the initial standard deviation has a lot to do with this. Certainly the size of the shift, right? If we want to detect a very small shift, 16.3 ounces to 16.29 ounces, I can do it statistically. It's just the price is I need a very large amount of data to shrink that distribution up. And then finally, this allowable level of type 2 error. In other words, what is the probability that the process will shift by a certain amount and yet my chart will not detect it on a given sample? So those are the three key things that are going to drive the sample size. There's a formula. You can take a look at this at your leisure. You'll see the D is the difference and sigma is the standard deviation, and these Z's have to do with the type 2 and type 1 error. This is normally fixed based on where we draw control limits at 3. Some of you might recognize Z values. If you're interested in this sort of level of detail, after the webinar, you'll be able to click on a link to a white paper that will describe the use of this formula. Another option, you will also have a little Excel worksheet that you can download, which simply allows you to put in the 3 key parameters that I just mentioned: the standard deviation. Now this will be the standard deviation of your individual measurements, the amount of the shift that you want to detect. These are in units of, in my example was ounces, but it would be millimeters or whatever your units are. And then the power, which is the probability that you will detect this shift, okay, if it actually occurs. And then this will just simply calculate the sample size that you need. Okay, so you have that available as well. And then finally, there's a table here just for some guidance. If you're just looking for a rough idea, if we sort of normalize the size of the shift and talk about numbers of standard deviations rather than the actual size of the shift and the actual standard deviation, we can just look at this as a sample size in a table. So essentially we have different powers, right? So if you want there to be less, no more than a 1% chance that you'll miss a signal, then depending on the size of the shift, these are the sample sizes that are required. And I guess one thing that jumps out at me here, if you look at, say, a reasonable power, maybe 95%, and you look at the sample sizes that are typically used on X bar charts, say 5, which is what a lot of people answered, the size of the shift that can be detected with a sample size 5 is a 2 sigma shift. That's a pretty large shift. Of course, it again depends on your capability and how much of a shift do you need to detect, but most charts of sample sizes that are typically used do not have great power to detect shifts very quickly. Okay, that's the key point. And with the last couple of minutes, I'll just show you these curves to you. Another tool that you can look at as a way to sort of summarize this idea is called an OC curve. It more or less just summarizes the calculations we just kind of went through, and really we'll just look at an example of a couple of OC curves. So it allows us to really investigate how does this power or type 2 error, whichever one you want to talk about, there's just one, there's one minus the other, how does it depend on the size of the shift that we're trying to detect and our sample size? So again, in general, the smaller the shifts we want to detect, the greater our type 2 error is going to be unless we increase our sample size, and then we can manage that. Conversely, the smaller the sample size we use, the higher the type 2 error probability, again, all things held equal. And on these curves, again, we're going to standardize the size of the shift based on the number of standard deviations. So what we have here on these OC curves are basically a bunch of them on the same picture here. So I essentially have a separate OC curve for about 7 different sample sizes here, 1 through 20. And what the OC curve does is it shows me the relationship between the size of the shift, okay, in numbers of standard deviations, versus the probability of not detecting. This is my beta or my type 2 error probability, or 1 minus the power. Okay, so we want this number to be low. We want to detect shifts, not detect them. So what we can see from this is, let's just suppose I take, so let me go to the next one where I've actually tried to zero in on one particular curve. So n equals 4 in this case. This is the blue curve. So what we can see is, suppose the size of the shift that I'm trying to detect, Fred, thank you for helping me with that. Size of the shift is 1.5 sigmas. So back like that ice cream example, I'd like to detect a 1.5 standard deviation shift. With a sample size of 4, actually, I have about a 50% chance of detecting and a 50% chance of not detecting that shift. Okay, so that's not very promising. It's I flip a coin. Don't use the control chart. Just flip a coin if that's what you're trying to do with a sample size of 4. Again, I'm being a little flippant because obviously we're not going to just take one sample. We're going to take multiple samples over time. But again, if you have a critical characteristic and the risk is high of not catching something, like you're controlling a critical ingredient and a medication, and you have very little tolerance for being out of control, especially if your sampling frequency is low, and this is your one chance to catch it, you better be increasing your sample size to something that's going to give you less of a risk. So if that's the shift I want to detect, these curves are suggesting maybe I want to use a sample size of 10, which would, make my type 2 error less than 10%. Okay. So that's the idea behind the OC curves. You can use this as a way to help design a chart and ask the questions, hey guys, this is our current capability. What kind of performance do we want from this chart? And by doing this, we can try to ensure that we're thinking about type 2 errors, that we're detecting shifts that are important for us to detect. And at the same time, this is a case where a bigger sample size isn't always better. The converse of this whole discussion is if you're using a sample size of 8 or 5, and your process is very capable and very stable, and maybe not super stable, but it's shifting small amounts, and that shifting is sort of almost expected because there's batch to batch or lot to lot variation or setup to setup variation, and you're reacting to these small process changes and calling them special cause when really you're not going to do anything and you don't care about it. You'd really be better off backing off on your sample size and trying to align the statistical properties of the chart with your practical objectives of why you're doing the charting in the first place. So with that, hopefully leaving a few minutes for some questions. I'll turn it out. I'll kind of open the floor here to the chat window, and Fred, if you have any comments you want to make.
Yeah, thanks, Stephen. I mean, I really like the idea where you had the two curves, and as you increase sample size, you could see the change in probability of detecting it. But I think one of the things is that as you illustrated it on the next sample you're taking, but if I understand the rules of control charting, I mean, the same logic applies. What's my chance of detecting the shift after 5 samples? In the same basic process that works, though, is because the chance of a signal is about the same for all of the rules. There's subtle differences between them, but whether I get a run, a single point out, or 2 points in that lower quadrant, the probability of those occurring is about the same. That's why they're a common set of rules like that. Am I thinking through that right?
Yeah, essentially, and I think you hit on a couple points. There's lots of rules that you can deploy. Of course, the more rules, the more false alarms you will see. Of course, the whole point of having some additional rules that we look for is it helps us reduce the effective type 2 error probability. We're not just relying on exceeding a control limit. And the other thing you brought up was, you could take the example we had, for instance, where let's suppose your type 2 error probability is only 50%. You could ask the question, what's the chance I'm going to not detect it, or at least detect it after 3 subgroups or 3 samples? So that would be like, the easiest way to do is 1 minus the probability that you don't detect it, which would be 0.5 to the third. So the truth be told, you have almost a 90% chance of detecting it after at least by the end of the 3rd subgroup. So you could go through these calculations and trade off, my frequency and my type 2 error probability on a given sample. Of course, a lot of those other rules you mentioned, they require 7 or 9, right? So you're not going to react necessarily very quickly, and if you're not sampling that frequently, you might have a fair amount of time elapsed before you actually can conclude that the process is out of control. So so those are some comments I'd have to the points you brought up, but they're good points.
Okay. Well, I changed the screen here to our kind of conclusion screen, and in the lower right-hand corner is the links button, and that's, Stephen, you mentioned that earlier, is there's, you can sign up for the list to receive notices of these webinars and other webinars in the reliability quality space. There's the white papers link, goes back to Integral Solutions site, and there's a lot of other good information up there too, besides just the white paper you mentioned, Stephen. Feel free to get in touch with Stephen offline, and I know he loves talking about this topic, so you can find him on LinkedIn. And same for me, if you want to stay in touch, we appreciate that. I don't see any other dominant questions. I see a bunch of thanks and thank you. Appreciate that, Kyle and Kefren and George. I'm glad you got something out of this. I know I did. I think, Stephen, your ability to illustrate, which could be a very complex statistical process, using the central limit theorem, and it certainly could have dove into derivations, but you made it very, very clear. Also makes me think back to all the mistakes I've made setting up control charts. So I'll have to.
I may have to go to a class using this tablet. I don't know if I want to draw again in the future, but yeah, thank you, Fred. I appreciate you producing this.
All right, well, we'll figure it out. And like we mentioned earlier, is that Stephen and I are putting together a full course on SPC and capability studies. There'll be more information coming out. There'll be chances to sign up for that. And we'll be using the same kind of platform and hopefully building in or expecting to build in a lot of interaction and dialogue and discussion. So George or Gregory, it looks like you got a good refresher there. That's great. Dave, appreciate it. Pat, well, you already know Stephen and his presentation, so, but I agree, it's a great presentation. So I'm going to shut off the recording here. I'm going to leave this screen up so people can get to the links and download stuff for a few more minutes.